Correlation is not causation. Things can move together. Always ask what causes it.
Welcome to the estuary census. Here, the landscape is a constant shift of rising tides and teeming life. Observe the shoreline during warm tides. The gulls grow numerous, and the crabs do too, their counts rising at the exact same time. But the gulls do not make the crabs, nor do the crabs make the gulls. A third factor, the warmth of the tide and the food it brings, lifts both populations at once. Two measures moving together is not proof that one causes the other. Maintaining this distinction protects you from making claims that the data cannot support. Near a great blue heron hunting in the marsh, we can test this logic against a common observation. In the summer, ice cream sales and sunburn reports both rise together. Does this mean that buying ice cream causes sunburn? No. A shared outside factor, hot sunny weather, affects both quantities independently. Because the sun drives both behaviors, the correlation between the two does not prove that one causes the other. Near the river otters, we find a relationship between two variables that is harder to untangle. Data from a school shows that students who carry heavier backpacks tend to be older. If we assume a cause, we would have to believe that carrying a heavier pack causes students to age faster. This is where we look for a lurking variable, a hidden factor explaining why these two measures move together. Pause the video. Look beyond the backpack and the age and try to identify the third factor that influences both. Physical growth and grade level act as the lurking variable. As students grow, they move into higher grades and gain the capacity to carry heavier loads. Without identifying that hidden factor, an association is just a starting point, not a conclusion. A red fox watching the vegetation reminds us that in science, we need a specific way to move past simple observation. Suppose a scientist wants to determine if a new fertilizer causes plants to grow faster. A simple scatter plot of plants in the wild leaves too many factors like sunlight and soil type uncontrolled. A controlled experiment isolates the test by changing only one factor, the fertilizer, and comparing it against a control group where nothing changed. This setup allows the scientist to rule out alternative explanations that a simple observation cannot. Because it is designed to test causation directly, the experiment provides evidence that a scatter plot alone cannot match. Across the estuary, many things change at the same time. The key is to recognize that while variables are correlated, that is not proof that one causes the other. This prepares you to interpret data and real-world claims more carefully. Ask yourself, does this correlation actually prove causation?